We now study modular arithmetic. So we let m and n be integers and let d be some positive integer. We say that m is congruent to n modulo d, which is written in this form. So this will be read m is congruent to n mod d if and only if d divides m minus n. So we're going to use this definition to determine which of the following statements are true. So is 12 congruent to 7 mod 5? Well, let's take a look and we go, well, 12 minus 7 is equal to 5. And that can be written as 5 times 1. Right? So by definition divisibility, that would mean that 5 divides 12 minus 7. And so hence this is a true statement. Now is 6 congruent to negative 8 mod 4? Well, we just do the same thing. 6 minus negative 8 is equal to 14. And 14 can be written as 4 times 3 plus 2. Well, this means that 4 does not divide 6 minus negative 8. Right? So this would imply that 6 is not congruent to negative 8 mod 4. And going back up to the previous problem, this would mean that 12 is congruent to 7 mod 5. And finally, is 3 congruent to 3 mod 7? 3 minus 3 is 0, and 0 can be written as 7 times 0, which means that 7 does indeed divide 3 minus 3, and so 3 is congruent to 3 mod 7. Now, we're going to list 4 equivalent statements. Let a, b, and n be any integers. Suppose that n is greater than 1. The following statements are all equivalent, meaning that any of these 4 statements say the same thing. Any of these 4 imply another one. The first statement is n divides a minus b. The second statement is a is congruent to b mod n. The third statement is a is equal to b plus kn for some integer k. The fourth, a and b have the same non-negative remainder when divided by n. So what we will do is we will show that 1 implies 2. So statement 1 implies statement 2. Statement 2 implies statement 3. Statement 3 implies statement 4. And then statement 4 implies statement 1. From this, we can then deduce that no matter what statement you have, it implies the remaining 3. So we let a, b, and n be integers with n greater than 1. The proof of 1 implies 2 is a very straightforward one. Suppose that n divides a minus b. Well, that's the definition of a being congruent to b mod n. And so that proof is complete. Now the proof that statement 2 implies statement 3. Suppose that a is congruent to b mod n. Then n divides a minus b, which means that there has to be an integer k such that a minus b is k times n. You can solve for a, and we get that a is then equal to b plus kn, and so that proof is complete. So the proof that statement 3 implies statement 4. Suppose that a is equal to b plus kn for some integer k. By the quotient remainder theorem, we have that a would equal nq plus r for unique integers q and r, with 0 less than or equal to r less than n. So this would mean that b plus kn has to equal nq plus r. Solving for b, we get b is equal to nq minus kn plus r, which means that b is equal to n times q minus k plus r. So r is the remainder when a is divided by n, and when b is divided by n, since r has to be unique. So they have the same remainder when divided by n, and so that proof is complete. And finally, the proof that statement 4 implies statement 1. Suppose that a and b have the same remainder when divided by n. Then a minus b would equal nq plus r minus nk plus r for integers q, k, and r, with 0 less than or equal to r less than n. So a minus b would equal nq minus nk. That equals n times q minus k, which implies that n divides a minus b. And so that completes the proof that statement 4 implies statement 1, and overall we have shown that these 4 statements are all equivalent. Now recall that by the quotient remainder theorem, when an integer a is divided by a positive integer n, a unique quotient q and remainder r are obtained with the property a is nq plus r, with 0 less than or equal to r less than n. However, there are exactly n integers that satisfy this inequality for r, namely the integers 0 through n minus 1. So we call this unique integer r that satisfies the quotient remainder theorem for when a is divided by n the residue of a modulo n. Right, so stated formally, given integers a and n with n greater than 1, the residue of a modulo n is the non-negative remainder obtained when a is divided by n. The numbers 0, 1, 2, 3, so on and so forth, up through n minus 1 are called a complete set of residues modulo n, and to reduce a number modulo n means to set it equal to its residue modulo n. If a modulus n greater than 1 is fixed throughout a discussion and an integer a is given, the words modulo n are often dropped, and we simply speak of the residue. So if n is any integer with n greater than 1, congruence modulo n is an equivalence relation on the set of all integers. The distinct equivalence classes of this relation are the sets class of 0, class of 1, so on and so forth, up to class of n minus 1, where for each a from 0 to n minus 1, the class of a is equal to the set of all integers m, such that m is congruent to a mod n. Now, when we were studying equivalence relations, we already saw several congruences. I believe the one we looked at was the congruence modulo 3. Right? We saw that they were indeed equivalence relations. Well, now we're going to prove it for a general n. So we're going to prove that this is true no matter what integer n we are given. And we're also going to prove the distinct classes. So there are 2 things that we need to prove. That the congruence modulo n is an equivalence relation, and that these classes are the distinct classes of the congruence relation. So here we're only going to prove that the congruence relation is an equivalence relation. The proof that these are the distinct classes will be left as an exercise. So suppose that n is an integer with n greater than 1. We show that congruence modulo n is reflexive, symmetric, and transitive. Right? Remember, that's what it means to be an equivalence relation. So the proof of reflexivity, suppose that a is an integer, then a minus a is equal to 0. This equals 0 times n, which means that 0 divides a minus a, which implies that a is congruent to a mod n. Hence, the congruence modulo n is reflexive. The proof of symmetry. Suppose that a and b are integers such that a is congruent to b mod n. Then by definition, this means that n divides a minus b, which means that a minus b is equal to nq for some integer q. So b minus a would be negative nq, which is n times negative q. And of course, negative q is the product of two integers, so negative q itself is an integer. So by definition, this means that n divides b minus a, and by definition, this means that b is congruent to a mod n, and so the congruence modulo n is symmetric. Finally, the proof of transitivity. Suppose that a, b, and c are integers such that a is congruent to b mod n, and b is congruent to c mod n. Then by definition, n would divide a minus b, and n would divide b minus c. So a minus b is equal to n q1, and b minus c is equal to n q2 for some integers q1 and q2. So b minus c equal to nq2 implies that b is equal to c plus nq2. And so if we now substitute this b into here, we have a minus b is equal to a minus the quantity of c plus nq2, which equals a minus c minus nq2. And that has to equal nq1. So a c is nq1 plus nq2, which is equal to n times q1 plus q2. Now q1 plus q2 is an integer, and so this means that n divides a minus c, which means that a is congruent to c mod n, and hence it's also transitive. So we can now look at modular arithmetic. Let a, b, c, d, and n all be integers, with n being greater than 1. And suppose that a is congruent to c mod n, and b is congruent to d mod n. Then a plus or minus b would be congruent to c plus or minus d mod n. A times b would be congruent to c times d mod n. And a to the m would be congruent to c to the m mod n for every positive integer m. So we're only going to prove the second operation. So we're going to prove the multiplication, the product operation. The other two will be left as an exercise. So suppose that a, b, c, d, and n are all integers, with n being greater than 1. And suppose that a is congruent to b mod n, and c is congruent to d mod n. Then there would exist integers s and t such that a would equal c plus sn, and b would equal d plus tn. So times b, by substitution, is c plus sn all times d plus tn. We now do algebra, expand this out, so that will give you cd plus ctn plus snd plus sntn. Well, these last three terms all have an n in common, so factor it out. So that would be CD plus n times CT plus SD plus STN. Right, well, this sum here is a solid product of integers, and so would itself be an integer. So by definition, or not rather by definition, but by the equivalent statements, this means that AB is congruent to CD mod N. That is what we wanted, and so the proof is complete. So we will now perform modular arithmetic to evaluate each of the following. So up here, 55 plus 26 mod 4, just add them together. So 55 and 20. So, I'm sorry. What we want to do first is write 55 is congruent to what mod 4. Right, so it would be 55 is 4 times 13 plus 3. So the remainder is 3. And so this would be congruent to 3 mod 4. Now 26. So 26 is 4 times 6 plus 2. So the remainder is 2. So 26 is congruent to 2 mod 4. So now we can look at 55 plus 26 mod 4. This would be congruent to 3 plus 2, which is congruent to 5, which mod 4 is 1. So this is what was meant by, we will typically leave out the mod. Right, I've said this is congruent to 3 plus 2. It's understood that it's all mod 4. So we look here, 55 minus 26. So this is 3 minus 2, which is congruent to 1 mod 4. 55 times 26 would be congruent to 3 times 2, which is congruent to 6, which is congruent to 2 mod 4. And finally, 55 squared is congruent to 3 squared, which is congruent to 9, which is congruent to 1 mod 4. Now let's compute 144 to the 4th power mod 713. So 144 to the 4th power would be congruent to 144 squared squared. So 144 squared is 20,736. So this is congruent to 20,736 squared. Now the remainder, when 20,736 is divided by 713 is 59. So this is congruent to 59 squared. 59 squared is 3,481. And when that is divided by 713, we get a remainder of 629. And so 144 to the 4th power would be congruent to 629 mod 713. Now 12 to the 43rd power mod 713. The idea here is to write 43 as a sum of powers of 2. So 32 is the largest power of 2 that is less than 43. So 16 is the next one. However, 16 plus 32 would be larger than 43, so we can't have that. After 16 would be 8. That'll give us 40. 4 would give us over 43. So plus 2 would give us 42, and then plus 1. Right, so this is 2 to the 5th, 2 cubed, 2 to the 1st, 2 to the 0. So what this means is that 12 to the 43 is 12 to the 32 plus 8 plus 2 plus 1, which would be 12 to the 32 times 12 to the 8th times 12 squared times 12. So 12 is simply congruent to 12 mod 713. 12 squared is congruent to 144 mod 713. 12 to the 8th would be congruent to 144 to the 4th power, right? It's 12 squared to the 4th. So 144 to the 4th is this number right here. And that would be congruent to 129 mod 713. And actually, if I'm not mistaken, that was the last problem, right? 144 to the 4th power. So I actually didn't need to do that work. Now 12 to the 32nd, right? So 32 is 8 times 4, so this would be congruent to 629 to the 4th power. So 629 to the 4th power is this number. And when divided by 713, that leaves a remainder of 485. So 12 43rd would be congruent to the product of all these numbers. So 485 times 629 times 144 times 12. So this gives this number. And when divided by 713, that leaves a remainder of 48. So 12 to the 43rd is congruent to 48 mod 713. Now, let's suppose that we wish to solve the following congruence for x. So we want to solve 2x is congruent to 3 mod 5 for x. Well, notice that 3 times 2 is congruent to 6, which is congruent to 1 mod 5. So it appears that 3 acts as a kind of inverse for 2 modulo 5. So if we multiply both sides by 3, we might be able to get a solution for x. And in fact, we can. Right, so we get 3 times 2x, which is congruent to x. This would be congruent to 3 times 3, which is congruent to 9, which is congruent to 4 mod 5. So x here would be 4. And we can always check that, right? 2 times 4 is 8, and that is 3 mod 5. Note that this only works because the congruence modulo is an equivalence relation. Right, and there I just said that, so that's a repeat. So this is our definition of inverse modulo. Given any integer a and any positive integer n, if there exists an integer s such that a times s is congruent to 1 mod n, then we call s an inverse for a modulo n. Now, not every integer needs to have an inverse. For an example, 2 does not have an inverse modulo 4. You can easily check this. do 2 times 0, 2 times 1, 2 times 2, and 2 times 3. You will never get 1 mod 4. So we will now examine how to tell whether an integer is guaranteed to have an inverse modulo n. So to start this, we need a new concept called the greatest common divisor. So let a and b be integers that are not both 0. The greatest common divisor of a and b, which is denoted as the GCD of AB, or sometimes just simply as parenthesis a comma b, is that particular integer d with the following properties. D is a common divisor of both a and b, and for every integer c. If c is also a common divisor of both a and b, then c must be less than or equal to d. So let's now compute the GCD of the following. So the GCD of 82 and 63. So to do this, the easiest way to do this, without the use of technology, is to write out each number in its prime factorization. Right? So 72 can be 6 times 12, which is 2 times 3 times 3 times 4. So I have 2 cubed times 3 squared. 63 is simply 7 times 9, and so that's simply the 3 squared times 7. So to determine the GCD, right, remember we want a common factor. Well, each term has 3 squared as a common factor. So the GCD would be 9. And there's no way another common factor, there's no other common factor to both of these that is also larger than 9. Right, so notice what I did. I looked for each prime factor and took the smallest exponent between them. Right? So the smallest exponent of 2 is 0, the smallest exponent of 3 was 2, and the smallest exponent of 7 was 0. So let's do the same general idea for b. So 10 to the 20th can be written as 5 times 2 to the 20th, right? Because 10 is 5 times 2, so it's 2 to the 20th times 5 to the 20th. And then 6 to the 30th is 2 times 3 to the 30th, so it's 2 to the 30th times 3 to the 30th. So the GCD of 10 to the 20th and 6 to the 30th is 2, and the smallest power is 20. And there's no other common prime factors, so 2 to the 20th power is the GCD there. Now we say that two integers a and b are relatively prime if and only if their GCD is 1. And we say that integers a1 through an are pairwise relatively prime if and only if the GCD between any two distinct integers, so between any two of these integers, is equal to 1. We are also going to need the well-ordering principle for integers. Let S be a set of integers containing one or more integers, all of which are greater than some fixed integer. Then S has at least one element. Or I'm sorry, then S has a least element. So there's a smallest element. With that, we can now begin to study when an integer is guaranteed to have an inverse modulo. So for all integers a and b, both not 0, if d is the GCD of a and b, then there exists integers s and t such that AS plus BT is equal to D. In other words, we can write the GCD of two integers A and B as a linear combination of the integers A and B. All right, so the proof of this, given integers A and B not both 0, and given that D is the GCD between A and B, define a set S to be the set of all positive integers X such that X is equal to AS plus BT for some integers S and T. We will first show that this set satisfies the well-ordering principle. Then this will reduce to just showing, this reduces to just showing that it's non-empty, since it is already a set of positive integers. So we just have to show that this is non-empty. If A is greater than 0, then we can write 1 times A plus 0 times B, and this is clearly in S. If A is less than 0, then we can write negative 1 times A plus 0 times B. This is clearly in S. If A is 0, then B cannot be 0 by assumption. And we can write 0 times A plus 1 times B is in S, which is clearly in S. Actually, this would be either plus 1 times B or plus negative 1 times B, right? Depending on whether B is positive or negative. And that would clearly be in S. So therefore, S is non-empty. It's always guaranteed to have an element. Now, since S is a non-empty subset of the positive integers, the well-ordering principle for the integers says that there must be a least element in S. Call it C. Then there would exist integers S and T such that C is AS plus BT, right? Because C is in S. We need to show that C is equal to D. And we do this by proving that C is less than or equal to D and that C is greater than or equal to D. Right? If a number is so if C is less than or equal to D and C is greater than or equal to D, the only way that can be a true statement is if C and D are the same number. So we start with the proof that C is greater than or equal to D. Since D is the GCD of A and B, D divides A and D divides B. So there would exist integers X and Y such that A is equal to dx and A is equal to dy. So now substitution, C equals x plus bt, which equals dxs plus dyt. This is equal to d times xs plus yt, where xs plus yt is an integer, and so d divides c. However, both c and d must be greater than 0. And as you recall, when we studied divisibility, we proved that this would imply that c is greater than or equal to d. Now the proof that c is less than or equal to d. So by the quotient remainder theorem, there exist integers q and r such that a is equal to cq plus r, with 0 being less than or equal to r, which is less than c. So r would be a minus cq. However, c is as plus bt, and hence we get r would equal a minus cq, which is a minus as plus bt all times q. I group the a terms together and then factor out an a. We have a times 1 minus sq and then minus btq. Now r is a linear combination of a and b. If r is greater than 0, then r is in S, and so r would be a smaller element of S than C, which would contradict C being the smallest element. Thus, we must have r equaling 0, and so A is equal to CQ, which means that C divides A. A similar argument, which is left as an exercise, establishes that C also divides B. Hence, C is a common divisor of A and B, but since D is the GCD of A and B, we must have, by definition, C less than or equal to D. And that completes the proof. Now, as a direct corollary of this, if A and B are relatively prime integers, then there exist integers S and T such that AS plus BT is equal to 1. This literally follows directly from the previous theorem by just setting the GCD to 1. Now we can look at the theorem of existence of inverse modulo n, which states for all integers A and n, if the GCD of A and n is equal to 1, then there exists an integer S such that A times S is congruent to 1 mod n. Hence, this means that S would be an inverse of A modulo n. And this is a very simple, straightforward proof. Suppose that A and n are integers, and the GCD between A and n is equal to 1. Then there must exist integers S and T such that AS plus NT equals 1 by the previous corollary. Subtracting NT from both sides will give AS is equal to 1 minus NT, which is equal to 1 plus negative T times N, where negative T is guaranteed to be an integer. So AS is congruent to 1 mod N by definition, and that completes the proof. So we now wish to find an inverse for 43 mod 660. So first, we'll check to see if an inverse is guaranteed. So we want to check the GCD of 43 and 660. However, we're going to do this in a little bit of a different way. So we're going to write out 660 as some integer times 43 plus a remainder. So 43 times 15 with a remainder of 15. So this would mean that 15 is equal to 660 minus 43 times 15. All we did was solve for the remainder r. Now we'll take this integer, 43, and write it as the remainder times some integer plus a remainder, right? So 15 times 2, and then plus 13. And then again, we'll solve for that 13. So this is 43 minus 15 times 2. Now we want to write 15 as quotient remainder theorem when divided by 13. So this will be 13 times 1 plus 2. So 2 would equal 15 minus 13. Now divide 13 by 2. We'll get 2 times 6 plus 1. So this means that 1 is equal to 13 minus 2 times 6. And 2 would be 1 times 2 plus 0. We now have a remainder of 0. So this is our GCD. So these two are relatively prime. Now we're just going to work in reverse. So we want to now try and write this as a linear combination of 43 and 660. So 1 equals 13 minus 2 times 6. But how can we write 13? We write 2 as 15 minus 13. So this 13 minus 15 minus 13 times 6. This simplifies to negative 3. That's not a minus 3. That should be a minus 13. So it's negative 6, positive 6 times 13 because it's negative, plus 13. So that's 7 times 13 minus 15. We now come back, we go up the next step. 13 is 43 minus 15 times 2. So 7 times 43 minus 15 times 2, and then minus 15. So this is equal to 7 times 43 minus 14 times 15 minus 1. So we'd have minus 20 times 15 . Right, so a quick correction up here, I forgot to write down 6 times 15. Right, so that's why this is the 20 times 15. Right, so now we come back and we go, well, that took care of 13, so now we want to write 15. So it's 660 minus 43 times 15. So 7 times 43 minus 20 times 660 minus 43 times 15. So this will equal 307 times 43. Should specify that's not a decimal, that's a times. And then minus 20 times 660. So this implies that 307 times 43 is equal to 1 plus 20 times 660. So by definition, this means that 307 times 43 is congruent to 1 mod 660. And so 43 inverse is congruent to 307 mod 660. So the inverse of 43 is 307. And that's how you find inverse modulos. Now this has wide applications in the study of cryptography, which I will not be considering in this lecture series. So with that, we're going to conclude our study of modular arithmetic. In the next video, we will look at partial order relations.